Okay, so guys, we are in our graphing chapter 7 and 8 book today, and we're going to go through 7.1 and 7.2. The good news is, if you read the blog, it says this. We're doing this because we have to cover it curriculum-wise. We're getting you to look at this. You might see graphs like this in your first-year university courses, but we're not going to test you on them. When we test chapter 7 and 8, we'll focus on the other book, and we'll focus on all of the algebra and arithmetic that we're going to do. We've tested graphing quite a bit this year already. Don't really feel the burning desire to keep on graphing and keep on testing the graphing. But what we need to see is we need to be able to recognize what exponential functions look like graphically. First of all, when we say an exponential function, again, we mean that the base itself is a constant and the exponent is my variable. So my function of x is some number to the power of x. And when you graph that, if the base is positive, it goes upward very sharply. And again, remember that anything to the power of 0 is 1. That's why it goes through 1. What if the thing I'm multiplying by itself over and over again is a negative? Well, again, it's going to be even a negative to the power of 0 is 1. So it's still going to go through this point when x is 0, y is 1. But it's going to be sloped downward, a downward curve. And notice for both graphs, the x-axis is an asymptote. Why is the x-axis an asymptote? Why can't you cross? Why can't y be 0 in the equation y is equal to c to the power of x? Well, think about it. Let's pick just an example. You don't have to write this down even. Suppose I had y equals, let's use the one from Al's allowance. Right? We're doubling over and over again. Give me a number for x that when you put it in, y will become 0. Notice that's impossible, right? If you put in 0, you get 1. If you put in a really big number, like say this x becomes almost infinitely big, well then y blows up, goes to infinity. But what if you put in a really small number? What if you put in even 0.00001? You're still not going to hit 0. And what if you put in a negative number? Do you cross into the negatives down here? No, because remember, that just makes a reciprocal. That's how negative exponents work, right? So there we go. That's what this says here. The domain when c is positive is that it go from negative infinity to infinity. The domain when c is negative, even if it's going this way, you're still going to negative infinity that way for domain. The range is still the same. Notice curved bracket, you can't actually touch 0, and you can go blow up forever. Oops, I didn't mean to make a mark there. Okay. And the same thing here, the range, it goes up forever, but it'll never actually touch 0, so curved bracket. And they both have an asymptote at the x-axis. All right, and two things that you maybe have already seen already, especially if you're in the AP version of either of these courses, is in physics, radioactive decay follows exponential growth patterns. And in biology, of course, bacterial growth. So we'll see those types of examples quite a bit. All right, let's do some graphing. Let's sketch the graph of f of x is equal to 2 to the power of x. So let's put some numbers to this, shall we? What happens? Let's go 2, 1, 0, negative 1, negative 2. All right, so that would mean that y is 2 to the power of 2, which is 4. This is 2 to the power of 1, which is 2. This is 2 to the power of 0, which is 1. This is 2 to the negative 1, which we just talked about. That's a half. This is 2 to the negative 2, which is a quarter. What do these points look like? Well, again, 0 and 1 makes a point. 1 over goes 2 up. 2 over goes 4 up. And here's that curve. By the time you're at 3, I'd be off this grid. I'd be up at 8. 3, so 6, 7, 8. So I'd be up there someplace. So I'm definitely curving up that way. But what happens this way? Well, at negative 1, I'm at a half. At negative 2, I'm at a half of that. If I went to negative 3, I'd have a half of a half of a half. That's an eighth. But I will never actually cross 0. I'll just get infinitely close to it. Note, the base is 2. The function is increasing as you go left to right. The graph passes through 0, 1. The There is a horizontal asymptote at y equals 0. Since y can't be negative, there is no number in the universe that you could make x be that would make a 2 times by itself and end up being negative. Even if you times 2 by itself a fraction of times, you can't get a negative number. And domain and range are from negative infinity to infinity for domain, 0 to infinity for range. A little bit of mathies here. The graph approaches the x-axis when x heads to negative infinity. Approaches doesn't mean it'll ever touch it. It just means it'll get infinitely close. What happens if we change the base up? Well, notice 3 to the power of 0 is still 1, so that point doesn't change. All that happens is this graph gets steeper. Instead of 1 becoming 2, 1 becomes 3. 2 becomes 9, so I'm already way up there someplace. It also heads to the asymptote faster, right? Because 3 to the negative 1 is a third, not a half. And then to the negative 2 would be a ninth, not a quarter. So it's just a steeper graph in both directions. Oh, I kind of missed my dot. I'll make a bigger dot. There we go. Ah, what if the base is a fraction? Maybe we should explore this one. If you have enough room, make an x and an f of x here, x and y. So what happens when x is, we'll use the same points, negative 2, negative 1, 0, 1, 2. Well, 0, that's the easy one. Anything. A half times itself 0 times. Anything to the power of 0, except for 0 itself, is 1. That point doesn't change. Okay. Next. Negative, well, let's go positive first. Anything to the power of 1 is itself. So at 1, we get a half. But what happens at 2? What's a half squared? That's like saying, what's a half of a half? You get that that's a quarter? So we're going this way. And then the next one would be an eighth. So et cetera, et cetera. What about when I have 1/2 to the power of negative 1? Well, what does that do? It reciprocals it, right? So that would equal 2. And what would 1/2, I'm kind of out of room. What would 1/2 to the negative 2 look like? Well, it'd be the reciprocal squared. So it's going this way. Sorry. There we go. And that's it for 7.1. That's the basics of it. That's basically what exponential graphs look like. Again, go look at the news, at the graphs of the daily number of infections, and you'll see this curved thing. Think about Al's allowance, right? Remember how the first week we barely made it past $1, and then all of a sudden, vroom, the numbers take off. That's how exponential graphs look. Okay? Here's how we transform them. This should look fairly familiar to you, right? A is, of course, just a coefficient. C here is my base. B, and of course, A could be my horizontal, or sorry, let me say that again, my vertical stretch. B, so why don't we actually start labeling these? A is my good old vertical stretch. B is my horizontal stretch. H is my horizontal shift. And K is my vertical shift. So, what's different about this? Ah, yeah, remember that from Al's allowance? That's how we calculated the total eventually, right? 2 to the power of x minus 1. So, what changes? We look back at the previous page, we just graphed 2 to the power of x. What changes about it when I do that minus 1? It just shifts the graph down 1, right? So 2 to the x minus 1. So originally, my graph went through here, but now it's going to go through here. And originally, my graph went 1, 2. Now that's going to shift down 1. Originally my graph went 2 becomes 4. Well, now that 4 is going to become a 3. Eventually, my original graph went 2 to the power of 3 makes 8. Well, now it's going to make 7, which is kind of off my grid, so I'll just kind of keep going that way. And remember that my original graph had the y-axis as an asymptote. Now, the asymptote is y equals -1. Think about why that is. How come y is equal to -1 as an asymptote? Well, because the only way that f of x could equal -1 would be if 2 to the power of x is 0. And we just talked about that. No matter how many times, big or small, positive or negative, you times the base 2 by itself, you're never going to get 0. There's no number of 2's you could multiply to themselves to get 0. So if this number can never be 0, this number can never be -1. So this becomes a half, this becomes a quarter, this becomes an eighth. I think you get the picture. Okay, now check this guy out. What does this negative do here? Here, I'm going to write this over here. So this has a negative here. What does that negative do? What does a negative on A do? Yeah, people are giving me a hand sign like they're flipping their hand over. Come on, you can say, use your words. She's drinking a coffee, that's why she can't use her words. Use your words. What's the word for it? Begins with an R.
Reflection.
The word we're looking for is a reflection, not reciprocal, it's reflection. So this is a reflection. Now, which one is it when it's on the A? It's a reflection in the x-axis. That is true. So now I'm thinking, I know 3 to the power of x. In fact, why don't I make a parent function? I'll do it really light. Give me a light color. I'll do this blue. My parent function is we go through here, and we'd go 1 over 3 up, and then we'd go 2 over, and we'd be up 9, which is way off the screen. And then this would be 1/3, 1/9. You get the picture. Oops, that's supposed to look like a curve. That doesn't look much like a curve. Let's try that again. There we go. So that graph there is going to get reflected in the x-axis. And then, what does this +1 do? Oh, guess I should get off of blue. That's a C value. It's a plus. But remember the opposite rule? We haven't talked about this in a while. It's been a while since we graphed anything. What does the opposite rule say here? Shift 1 unit. Look at the formula even. That's a minus h, which means this is minus -1. Good. This shifts, whoops, 1 unit left. So take this number here, reflect it in the x-axis, then shift it 1 to the left. Boom. There's my 0, 1 point. Got moved. Let's take this point here. Reflect it in the x-axis, then shift it 1 to the left. Take this point here, reflect it, and shift it 1 to the left. Take this point, reflect it in the x-axis. So 1, 2, 3, 1, 2, 3, but then move it 1 to the left. Ugh. Hang on. Oh, no, undo. Put that back. Change me to the small eraser. There we go. And I can erase part of the line I just made. There we go. Just want this to look pretty. I don't mind that. There we go. All right. Let's take a look at g of x here. What's this negative telling me? That's going to be my reflection in the y-axis. Aha! Okay, so once again, maybe I'll put the parent function down. If I was just going to graph y, oops, that was supposed to be blue. If I was just going to graph y equals 4 to the x, what's it look like? That's my parent function. Well, it still goes through there, because 4 times itself, 0 times is still 1. 1 becomes 4. Negative 1 becomes a quarter. Negative 2 would be a 16th, which is so tiny the dot's bigger than that. So, very steep. There we go. Very sharp curve. Nobody was doing any social distancing on that one there. That curve took off on them. Okay, so now let's put the reflection on it. So if we reflect this number in the y-axis, oh, it's on the y-axis. What does that mean? It means it doesn't move, but it still goes +1. What does the +1 mean again? Vertical shift up 1. So this point here moves up to here. This point here reflects in the y-axis, then it moves up 1. This point here reflects in the y-axis, and it moves up 1. This point here reflects in the y-axis, and it moves up 1. My asymptote does too. Normally this is my asymptote. Oh, this is my blue line asymptote right here. Well, the asymptote gets moved up 1. Because now I can't possibly have the function equal 1. Because for the function to equal 1, 4 to some power would have to be 0. Good luck with that. 4 to any power can't be 0. So there's my new graph. All right. So my parent function for the third one is going to be y to the 3x. So let's see. Goes through there. 1 becomes 3. 2 becomes too high. It's 9. Then a third, a ninth. Let's make the curve. Curve it, a curve it, a curve. Curve, curve, curve. What do you think that 2 does? Well, this 2 means that my 3 to the 2x means x values are, who wants to finish that sentence? Again, it's opposite rule. They are divided by 2 or multiplied by a half, whichever way you like to think about it. So here's an x value of 0. Well, that's not going to change, is it? Half of 0 is still 0, so this point doesn't move. Here's an x value of 1, which means I would like to multiply that 1 by a half. So it's now here. Here's an x value of -1. That value gets multiplied by a half, so it's now here. Here is -2. Multiply -2 by a half, you get -1. So it actually scrunches the graph. There we go. I'll give you a sec to catch up to me. I know I'm drawing fast here. And of course, you know where we're going from here, right? Now we're going to put several of these transformations together into one graph. Can the people at home hear Miss Cecily across the hall? She's very loud. Her voice really carries, eh? Okay, that's the most crooked asymptote I think I've ever made. Hopefully everybody here could make a much flatter asymptote than that. That's terrible. All right, let's move on and let's do a bunch of them. Okay, so we've got ourselves an A value, a B value. Actually, no, we don't really have a B value. B is still 1. We have a well, actually, wait a minute. I've already forgotten. What do we use? Yeah. C, remember C in this case is my base, right? So the base here is 3. My H value is positive 1, right? Because I'm minusing H. And my K value is 4. So what do all those things mean? Let's go back to the words on that. Let's use our words. 2 is a vertical stretch, or multiply y values by 2. 1 means don't do anything to the x values. The 3 is my base. This is, of course, means shift 1 unit to the right. And this 4 means shift 4 units up. But on an exponential graph, it actually tells me something else. It tells me that my horizontal asymptote t is y equals 4, right? Normally, on a y equals something to the power of x graph, the x-axis itself, which is y equals 0, is an asymptote. But again, this thing here, 3 times itself any number of times you want, can't be 0. So this thing can't be 0, so y can't be 4. So why don't we put that down first? There is my new horizontal asymptote. Right? Ugh, you know what? Can I make a change on this? Because I just realized this is going to suck to draw. Can I have a mulligan on this? Who wrote these notes? It's probably me. Okay, can we make this a -4? Just makes our lives easier. So that means we're going to shift this 4 units down, and our asymptote is now -4. There. Now we've got a whole big grid that we can play with. That's the way a smart person would have made these notes right there. Can we change that? Make that a -4, please. Okay, so now what? Let's see. Maybe not a bad idea to draw your parent function again, right? Parent function is y equals 3 to the power of x, right? The base with just a simple exponent on it, which again goes through here. 1 becomes 3, 2 becomes 9, which is too tall, 1/3, 1/9. You get the picture. There we go. Okay, so our y value, let's take this point here for, let's go back to black. Let's take this point here first. Our y value is going to get multiplied by 2. So here's 1. 1's getting multiplied by 2, so now it's up to here. Then it is shifting 1 unit to the right, and 1, 2, 3, 4 units down. Remember, if you have a piece of loose leaf or something, you could do this. Remember, we used to be able to do these things here, right? We used to do our, I've forgotten what this is called. Our mapping notation. Thank you, our mapping notation. So our mapping notation, so 0, 1, our first step was, of course, to make it 0, 2, right? Because we multiplied, let's see, can I make that smaller so you can see the instructions? Yeah, there we go. So we multiplied the y value by 2. Then from there, we shifted it 1 unit to the right, which makes that 1, 2. And then from there, we shifted it 4 units down, which is 1, and then 2 minus 4 is -2. And that's where we are. We're at 1, -2. So if you're ever not sure, feel free to just take a point and go through all the steps one at a time. Here, let's do it for the next point. We start with the point 1, 3. Okay, what was the first step? Multiply y values by 2. Okay, now we got 1, 6. But then shift 1 unit to the right. So now we got 2, 6. And then we can shift 4 units down, 2, 2. So this point up here is now here. All right, let's do one more. Let's do this one. Ooh, this one's got a fraction. We ain't afraid of no fractions. Are we? I don't think so. Step 1, the y values get multiplied by 2. What's 2 times a third? 2/3. Step 2, shift it 1 unit to the right. Step 3, shift it 4 units down. What's 2/3 take away 4? Well, that positive 2/3 cancels negative 2/3, and it leaves me with negative 3 1/3. Might as well leave it as a mixed number. It's easier to think about graphing wise. So 0 for x and negative 3 2/3 for y. So there we go. We're getting close to our asymptote now. I think we can graph it from here. We curve up. That's supposed to be a curve. And then we approach our asymptote that way. Something like that. Should be a little smoother than that, obviously. All right. One last thing. Don't forget. Oh, write the equation of the asymptote. Oh, I kind of did that up there. Y equals -4. There. Don't forget, we did have function notation for our equations too, right? If f of x is equal to 3 to the power of x, if that's my parent function. Wrong class, that would have been slot 2. We had a class change while you weren't looking. It's all good. Okay, so is this right? Oh, no, it's not. Sorry, we actually must have changed the notes. This should be a minus. What should this? Okay, fix this. Obviously, this was a different example. What should this be? If the original function is f, what are my changes? Cross that out. Y equals, what did we do first? We doubled the y values, and then we shifted 1 unit to the right, and then we shifted 4 units down. So there we go. Sorry about that. That's a typo in the notes. I think this used to be the example before we changed it. And then I just changed it again by making that 4 negative so that we could actually fit it on the grid. And there we go. There we have it. That's all there is to it. That's applying your Unit 1 thinking to exponential graphs. Okay, so I can stop the little lesson there.